Assalamu alaikum. In today's lecture, we are going to study the power transfer in terms of surge impedance loading. So from the last lecture in which we have derived the formulas for the complex power flow through the transmission line, we have derived a three-phase real power formula for the lossless line, which was P3 phase is equal to VRL VSL divided by X dash sine delta. So here this real power is actually equal to the receiving end voltage and the sending end voltage multiplication divided by the X dash, which is the transmission line reactance, and sine delta, where delta is the load angle or the rotor angle. Load angle or rotor angle. So this was the formula that we derived for a lossless transmission line. And in order to get the maximum power transfer value, you have to put delta is equal to 90 degree, because sine 90 is equal to 1. So this three-phase real power will become maximum whenever we have delta is equal to 90 degree. And also for the lines, the load angle is actually equal to somewhere between 30 to 45 degree. So this is the load angle for the transmission line, and in order to get the maximum power transfer, you will have to put delta equal to 90 degree. Now, just to revise, from the previous lecture, we know that Vs is equal to cos beta L Vr plus JZC sine beta L IR, and the sending end current is equal to 1 over ZC sine beta L VR plus cos beta L IR. So these are the two equations that we derived for the sending end voltage and current in terms of receiving end voltage and receiving end current for a lossless transmission line. And here A is equal to cos beta L, which is the constant multiplying with the receiving end voltage. Similarly, B is this value, ZC sine beta L. C is equal to 1 over ZC sine beta L, which is this value, and D is equal to cos beta L. And we also know that A and D, these are the dimensionless quantities, and B is actually the impedance value because its unit is ohms, and C is the admittance value because its unit is Siemens. So we can say that this B value is actually the X dash of the line, which we will use in this formula. Now from this part of the equation, we will get that X dash is equal to ZC sine beta L when we are considering a lossless transmission line, when the line is lossless, right? So I'm writing this formula again here. With some modification, this three-phase power formula will become VRL divided by V rated. In order to convert this receiving end voltage into per unit value, VSL divided by V rated sine delta over ZC sine beta L. So this is X dash value, right? So in order to convert this receiving end voltage and sending end voltage into per unit values, we have divided it with V rated. So now we have to multiply it with V rated square, so that this V square will cancel out with this one. So there is no change in the actual formula of P3 phase, that was this one, right? And from the previous lecture, we know that surge impedance loading is equal to V rated square divided by ZC. And putting this formula here, this is your V rated divided by ZC. This will be surge impedance loading. This will become per unit value, and this will also become per unit value. So the final formula for P3 phase will be equal to VR per unit Vs per unit sine delta over sine beta L into surge impedance loading. Here this is delta, which is a rotor angle or load angle, and in order to calculate this beta L, we know that beta lambda is equal to 2 pi. This beta is the phase constant, and this lambda is actually the wavelength. So whenever you are measuring the phase constant over the whole wavelength, the angle should be equal to 360 degree, which is 2 pi, right? So this will become beta lambda L into 2 pi L, and the final formula will be beta L is equal to 2 pi L over lambda. So whenever you are using this equation, you will use beta L value, which is equal to 2 pi L over lambda, right? So the final formula for P3 phase real power in terms of surge impedance loading will be VR per unit multiplied with Vs per unit divided by sine 2 pi L over lambda. And this formula is frequently used whenever you are designing some transmission line, and this will be explained by using a simple example. For example, in this case, we have to build a transmission line which has to transmit a 3-phase power of 700 megawatt. The length of the line is 315 kilometer. The sending end voltage is 1 per unit and the receiving end voltage is 0.9 per unit. So in this design, we are actually following the standard EN 50160, which says that the voltage value should be within the limits of plus minus 10% of the nominal value of the voltage, right? So the minus 10 value is 0.9 per unit. Lambda is equal to 500 kilometer and ZC is equal to 320 ohms, and for delta for the transmission line is 36.87. As I mentioned earlier, the load angle for the transmission line is somewhere between 30 to 45 degree. So in this case, we are assuming that is equal to 36.87 degree. Now we have to calculate the nominal level of transmission line voltage in the first part. Nominal level of transmission line voltage. And in the second part, we will have to calculate the theoretical maximum power that can be transmitted through this line, right? So from the formula that we derived earlier, we know that P3 phase is equal to VR per unit into Vs per unit divided by sine beta L into sine delta surge impedance loading. So I'm just writing it here because it will be used in the calculations. Now what we have to find in the first part is V rated, the voltage at which the power will be transmitted. And first we should have a formula which has V rated in it, and from the surge impedance loading formula we know that that is equal to VR square over cell. So this is your V rated value. So this will become VR is equal to under root ZC into cell. So this is surge impedance ZC, the characteristic impedance of a line when it is considered lossless. So the characteristic impedance of a lossless line is known as surge impedance. So this rated voltage has to be found, and we have to first calculate ZC and surge impedance loading. But from the question we already know that the surge impedance or the characteristic impedance of a lossless line is 320 ohms, but we do not know the surge impedance loading formula. the surge impedance loading value. So from this formula we can easily calculate the surge impedance loading value, because we know that we have to transmit the three-phase power which is equal to 700 megawatt. The receiving end voltage is 0.9, the sending end voltage is 1 per unit. Sin beta L, we have to calculate the beta L value and the surge impedance loading value. So first, to calculate the beta L value, we know that beta L is equal to 2 pi L over lambda, right? So 2 pi is equal to 360. Length of the line is 315 kilometer, and the lambda that is given in the question is 500 kilometer. So this will give you the value of beta L, which is equal to 22.68 degree. You will use this in this denominator. And now you already know all the variables in this equation, so you can easily calculate the surge impedance loading value, which will be equal to 499.83 megawatt. And lastly, you will use this surge impedance loading value in this formula of the V rated, and you will get the voltage, rated voltage of the line, which will be equal to 400 kilovolt. Because ZC we already know this is equal to 320 and SIL value is 499.83 megawatt. So the rated voltage of the transmission line in order to transmit the load of 700 megawatt is equal to 400 kilovolt. Now in the second part, you have to calculate the maximum power transfer, theoretical maximum power transfer value. For that, you know the formula of three-phase power transfer, which is equal to VRL VSL over X dash sine delta. And for the maximum power transfer, this delta should be equal to 90 degree. We know the VRL value, that is 0.9, VSL is equal to 0.1, and X dash is equal to ZC sine beta L, which is actually equal to the B constant of the transmission line. And ZC is equal to 320. Beta L we have calculated here, it is equal to 22.68. So this value will become 123.39, and the final value of P3 phase, the maximum theoretical power that can be transferred through this transmission line, is 1167 megawatt. So this is a simple example that is related to the calculation that we have done in the first part of the lecture. Thank you.